Okay, so my name is Richard Conway. My Twitter handle is Azure Coder, so if you're interested in big data and machine learning, then please follow me. Today, I'm going to be talking about Azure services for big data and covering the scope of the Microsoft service Hadoop on Azure, and really talk about how to use it, provision it, and I'm also going to be talking about some advanced data scenarios. So we're going to be talking about how to use big data services interactively. We're going to be talking about aspects of real-time data. We're going to be talking about machine learning and some of the capabilities of being able to distribute machine learning across Hadoop services. So the agenda today is to look at building an HD Insight Hadoop cluster using Platform as a Service and PowerShell scripts. And then we're going to be querying data on that HD Insight cluster, and we're going to look at a lot of advanced use cases after that. So we're going to essentially focus on some new frameworks which integrate very well with Hadoop, such as Apache Storm and Apache Spark, and we'll be touching briefly the new Azure ML service, but only in the most pecuniary manner, because that's being covered in another session. Okay, so we'll talk about everything that underpins big data, and within Microsoft Azure, we really rely on storage, and thankfully we have a very advanced storage system with Azure Storage, which allows us to store up to 500 terabytes of data per storage account. And this gives us scope to store data in the petabyte range, which is fantastic, because it means that all of the sales data that we can accumulate as a company or business intelligence over the years can actually be processed with a Hadoop cluster, because we have a place to store it, and store it very cheaply. Blob storage. It's been around essentially since the beginning of Azure, and the understanding of the constraints and the levels of IOPS, how capable it is, we really understand these facts very well. There are 3 copies of data that it stores. We can essentially also use replication, so we can end up storing 6 copies of this data. So here's some statistics around storage. Essentially, we on a single blob we can get statistics of 60 megabytes read and writes per second. So we'll need to break this apart into small blobs and data sets, and with Hadoop we'll also need to build a partitioning strategy within storage, so that we can maximize the throughput of data that's being ingested by HD Insight. So if we look at these statistics, 60 megabytes per second per blob on a single machine will allow us to read that blob, a gigabyte blob, for over 16 seconds. A terabyte will take 4.5 hours, but a petabyte of data, which people are commonly talking about petabytes as this storage availability increases, especially with the resurgence of cloud computing. That will take us 6 months. So Hadoop is all about taking this fact of being able to read this data and execute it on a single machine, and then scale that up linearly. So if we consider what would happen if we had the same operations on 1,000 machines, 16 seconds would now give us 1,000 gigabytes of reading, or 160 milliseconds per gig. A terabyte would be 16 seconds, and we'd be looking at 4.5 hours for a petabyte. So you can see that scalability from 1 to 1,000 really does change the nature of the way that we can handle data, and HD Insight was specifically designed for that. And as you can see, the companies like eBay already have petabyte scale data. Okay, so what is HD Insight? It's basically the managed Hadoop service on Azure. It runs on Windows in Platform as a Service, and you can scale as many data nodes as you want to be able to have the scalability that we were talking about. Normally, Hadoop uses a local file system called HDFS, which exists across the cluster. It's a highly available, resilient file system, but due to the design of Azure, we get very, very good performance from blob storage. And so it's really a good thing for us to take all of our data assets and store them externally, especially due to the way that that HD Insight is configured, and Azure is configured, because essentially we have this concept of flat network storage, which ensures that compute and storage are as close to each other on a network level as they could possibly be. So we end up with very, very fast access to data. The other thing to bear in mind is that when we externalize data, it allows us to just create a cluster for a short amount of time. So if our data is residing on all of our data nodes, then we don't necessarily have to worry about shutting it down and losing that persistence on the disks. And HD Insight also provides additional services such as HBase, which is a column-based NoSQL store. One of the key things with HD Insight and Hadoop is that it's effectively stateless. So we'll describe some MapReduce jobs, and MapReduce jobs effectively act as pieces of software that can pipeline data and transform it from one state to another continually. But in between, you have no state. So HBase is one of the things that can be used to actually accommodate this state, so that you can have a fairly performant system of being able to read data back from HBase in between these sequential MapReduce operations. So there's very good support for managing Hadoop clusters. Essentially, what we're now calling the old portal has very good support for this, and you can manage all of your HD Insight clusters. The new portal also has support for this, but rather interestingly, there's a very, very rich set of APIs, so you can access HD Insight, manage it, all of the different types of services programmatically. And you can do this through PowerShell, you can do this through the Node.js command line interface, and you can also do this through .NET SDKs. So there's a variety of ways that you can actually interact with it. So rather interestingly, once our data is in storage, HD Insight has a variety of open source frameworks which it can apply to this data. And we can use expressions of logic over this mass stored data. And the other key aspect, which I think customers are really in tune with when they use the cloud, is that they just want to do batch processing with HD Insight, and they like to use it for a short amount of time. And given that, essentially having the data stored externally means that they can use that programmability that we described to create the clusters, to process their input data, to restore the output data in storage, and then shut down that cluster. And then if that's going on through the night, then in the morning there'll be a bunch of output data ready for them to report on or do whatever they need to do with it. So applying these expressions of logic within HD Insight, you could use frameworks that are part of this, such as Mahout, which is a machine learning framework we'll describe later. Also Apache Giraffe, which is a graph engine. Pig and Hive, which are respectively data workflow languages, and Hive is very much familiar to SQL developers. It's a set-based SQL-like syntax. And my personal favorite is being able to write expressions in C#, which has been a Microsoft innovation. And all of these are acted on through Hadoop within blob storage. And these clusters can be provisioned using PowerShell, and we can output in a variety of formats. So Azure blobs is the native output format, but we can also use tables and SQL database to read our output data from. There are a couple of other features within HD Insight which make it a really, really cohesive Hadoop platform as a service. There's state management. So by default, if you're using Hive to create tables to look at this unstructured data that you're ingesting, you can store the metadata of what that table looks like in a SQL DB. You can also use that same SQL DB to store configurations for things like Uzi, which are a workflow detail, which chain all the MapReduce jobs together, and how you actually output your data in what forms. And then the other really amazing thing is that there's a very rich logging framework attached to HD Insight. So you understand what clusters are doing. Because Hadoop is a command line tool, all of that command line, the standard in, the standard out, is all put within blob storage, and it's very, very easily accessible. And there's some rich metadata that's stored in table storage, so you have a complete understanding of what the cluster has done when it's finished its work. And as I said, you can query your data in .NET languages, Java, Pig, and Hive, and we can effectively create a job which contains a number of tasks, and that job is the high-level unit, and the tasks are distributed across a number of data nodes. It could be one data node, it could be 500 data nodes. Hadoop will manage that from job trackers and task trackers. We can apply a schema at execution time, so we're not bounded in the same way that we are with a SQL relational database. We can aggregate data that we have, we can filter it, we can pipeline data from job to job, storing intermediate outputs and then ingesting those intermediate outputs within the next MapReduce job. We can input from a variety of formats, we can output to blob storage. We've even got a tool within the Hadoop ecosystem which can take the data that our Hadoop job has done, and it can push it directly into SQL. And this tool is called Scroop. And one of the fantastic innovations that Microsoft has done recently is to enable Power BI. So when we've done these Hadoop jobs, a great way of visualizing this is using Power BI within the Office 365 framework. And as we can see here, we essentially can look at HD Insight as a commodity, because we've commoditized the ability to query something, and that's something that we can even put a cost to. So we can define how much it costs us for once to do a particular job, because we only need that cluster for a certain amount of time. We know how long that query is going to take to execute, and then we can deliver the results. There are some really interesting ways of creating very high throughput mechanisms to ingest all of this data from blob storage. There's some performance guidelines around virtual hard drives, which are 500 IOPS, and there are performance guidelines around storage accounts, which are 20,000 IOPS. So you can essentially mix and match how you put together storage accounts and where you store your data to effectively get the utmost throughput capability to HD Insight.
In this demo, we will show the process of provisioning a HD Insight cluster using PowerShell. First of all, we are going to be using PowerShell through the integrated scripting environment IC. And in this environment, we can see a script which we've pre-written, and we'll run it and we'll see the results in the bottom bar of the screen down here. Furthermore, we are using a well-known Azure subscription called Elastic Cloud Demos. Now, if we go into that subscription, we can see that this is a completely empty Azure subscription with no currently provisioned services. And that means that everything that we do to be created in here will happen from the script and nothing else. The process of the script are to select this subscription, to set some details about the name of storage accounts and the location that we should be building the storage accounts. We will then run through a process of securing, configuring, and then provisioning HD Insight, a cluster of HD Insight Hadoop, to then be available for later querying. While the provisioning is happening, we will go back to the slide deck and we will see a little bit more of the theory behind HD Insight. Then we'll come back to querying when this has been provisioned completely. So without further ado, let's begin by simply running the script, and I shall show you what it's doing at the same time. We run the script, and the first thing it's going to do is select the subscription that it should running, and then it's going to go and print out the one that's been selected. You can see at the bottom that the current account has been printed to the screen. Now it's going to create for us a storage account which is named cluster prefix, which is Azure Conf, and then a time string. If we go back to the Azure portal and we go to the storage section, Azure Conf, here we go. So if we go back to our script, we can see that this has been successful and we've got a key which has been printed out. We can now use this key for anything we want. This is the equivalent of going into here and managing the access keys within the Azure portal. The secondary key is shown here. We're now being asked whether we want to optionally add in additional storage accounts. But before we do that, we should have a look at what else has been prepared for us. We have a username and password converted to a secure string and then creating a PowerShell credential for our use. This is a credential that we will use when we connect in to the Hadoop services that are installed for us on the HD Insight cluster. We've configured a name and a number of nodes. The name is simply HDI, and then the previous name that we saw earlier, so that will be Azure Conf 203354. The fully qualified storage account name is also computed. Some configuration, which will be core Hadoop configuration. If you're familiar with Hadoop, this is the core site XML file inside the distribution of Hadoop you're installing. These are being appended into that file that will actually override any values that you match with. So we're currently here setting the compression codec to include gzip, the default codec, and the bzip2 codec. And we're also allocating 2 gigabytes of sort memory. You can set anything in here that you want to tune the HD Insight cluster to your specific workload. We're also creating MapReduce configuration, and then we're going through and creating information around what the basic settings of that should be. We're now at this stage here, which is checking whether or not we should add additional storage accounts. This is useful, as we'll see in a moment, for sharding strategies where we want to improve the throughput of our data. So we're now going to create multiple attached storage accounts. And if we check in the Azure portal, we will see those being created there as well. As you can see here, these accounts are now becoming available. We're now running all the way down to creating cluster here. The all-important execution here is the new Azure HD Insight cluster commandlet, which does all the work for us. Following this, which could take between 12 and 18 minutes, there will be a small process where we upload any data we find relative to our executing script. And we do that using the very simple Azure commandlet set Azure storage blob content. If we go back into the Azure portal, we will have a look inside the HD Insight tab. And as you can see, inside the Azure portal in the HD Insight tab, there is a brand new cluster, HDI Azure Conf, and the same date stamp that we had earlier, ready for us to, well, being provisioned for us so that we can later query. So if we go back to the slides now, we can come back to this cluster once it has been fully provisioned. In this demo, we're going to explore options for querying the data held in blob storage. And we're going to focus on the Hive language for SQL-like access to many terabytes of data you may have inside your cluster. So, first of all, we'll go back to the Azure Management Portal, and we can see that we have HDI Azure Conf 203354 running still in our account. We can go in there and see a little bit more information. One of the interesting things you get on this page is a link to the cluster itself over HTTPS, the name of the cluster followed by azure-hdinsight.net, and then if you go to that address, you will be prompted for a username and password. The username and password that you should enter are the ones that you provisioned the cluster with. So if we go back here, we can see that we used Azure Coda, and then the password of I wish I had a bigger broom. If we go back in here and type them in. And once this is loaded, we will be given the Microsoft Azure HD Insight management portal, and this on-cluster portal allows us to submit Hive workloads, see the results, interrogate what we have available for us on the cluster. So we begin simply by giving a query name of Hive sample1, and then submitting the standard Hive sample table select everything query that will go off in the background and will create us a job and will give us other results back from Hive. The Hive sample table, which is packaged with Hadoop, has got a set of sample data available for us to query that relate to users of a particular website and the type of device that they're using. As the page refreshes automatically, we will see the state updating from initializing to running, and then we'll complete eventually. So this is a page which automatically updates. We just sit here until the execution has concluded. And you can see that this is now completed. If we click on the query name, we get information about that particular job. It tells us what we executed. It gives us the example, the result set here. It gives us the ability to download that entire result set if we so chose, and it gives us some of the log for that. You can see that this took 24 seconds on this small cluster, and that parsed 60 or so thousand rows of data. This is a very convenient way of interrogating and using Hive. I'll show you a couple more examples on here before we go and show you what PowerShell can do. Next, we can try something a little bit more complicated and use a different data set that's available for every HD Insight cluster created. If we first go into the file browser, we can see that in the default container, we have had an example table created for us. An example data sample log. This sample log, which if we chose to download it, we could see it contains log4j type messages with some sample, some debug, some info, and some errors. We can see that actually it's quite hard to really work out what's going on in here. So what we might choose to do is use Hive to make that a little bit simpler. To do that properly, first of all, we go into the Hive editor and we have to create a table which defines a schema that will apply over the top of that log file. Firstly, we give a query a name. And we can create an external table over the top of this file held in the location example data. Now, the create statement is very simple, similar to standard SQL. And the only addition is that we have the external notified, say that it's located in a certain area of our cluster, or in this case on blob storage. So if we submit this job, you can see that the job is currently initializing, Now it's running, and that will be creating a table which will be held locally on this cluster, so it will go away when we delete the cluster. If we wanted to reuse the table multiple times, we have the option of applying at provision time something called the Hive Metastore, which allows us to centralize the storage of these tables in a SQL database service inside Azure. You can now see that this job has completed. If we wanted to go and see information about that, we can see that there was no output. This is simply a create statement, and we can see that actually there's a very simple log here with not particularly much information again. We hope that it succeeded. If we wanted to detect that has succeeded, we can go into here and say that we wanted to run the query show tables. That commands Hive to query its own metadata and show us what's available for our later querying. And that is now completed. Again, if we wanted to go into the show information, we can see that the available output now, the available jobs shown in the job output are Hive sample tables and log4j logs. This is the table that we created with our previous statement, log4j logs. Now, if we were to go back into the Hive editor, and if we quickly inspect that table, we can say describe table log4j logs. Submit that job. It will tell us information about that table. It will give us the metadata of that table so that we can then understand how we can query it. Now, we've just created this table, so it doesn't necessarily mean that we've immediately forgotten what's in that table, but this is a good way to discover information around your data. Maybe someone else on your team has created a table and you want to work out what's in there. Well, you could just do select star from there, but you wouldn't necessarily get all the information you need, like the types of objects and things. And if you say describe table, then that will do that operation for you. And here we can see that the log table has got these columns T1 through T7. Not particularly useful, but I thought I'd show you that anyway. Now if we go back to the main editor, and we might want to do a simple select statement from there. But here's one I prepared earlier. Which if we submit very quickly up, we will have the severity, the count of severity, where the severity is actually in the error state and grouping on top of that particular column. That is now completed. If we go into the query details, we can see that there were 3 in the error state. Now we could go on to have a much more comprehensive query, joining in additional data sets, having further applications than the simple group we have now. But this is simply to demonstrate that it's very, very simple for us to project logic over the top of data held in flat files. You can do this over terabytes of data, but actually, if you had a simple operation you wanted to do regularly and you were considering rolling your own text parser or an inspector, well, Hadoop and HDInsight brings together retry logic and other really advantageous technological fundamentals that would mean that you should maybe consider using what comes out of the box with Azure. It's very easy to provision, and it's very, very easy to actually command remotely. You don't have to use just the HDInsight portal. So let me just copy the simple query we have here and show you what I mean. If we drop to PowerShell, and so if we go back to our earlier IC window, so now that we've come back to the PowerShell IC that we had earlier, we can easily say that we want to know all the Azure clusters that we have available, and we just do that by specifying get Azure HDInsight cluster, which will, with no parameters to restrict, it will just go and get everything that's available. Here we only have one, and what we want to do is say use Azure HDInsight cluster. That use means select as the default and connect to that HDInsight cluster using the username and password that we know from earlier. The way PowerShell knows that is by using the management certificate with Azure to handshake behind the scenes. So we want to say that the name of the cluster that we want to connect into is HDI Azure Conf 203354. And it now says that it has successfully connected to the cluster. That means it's also the default, and we can just submit anything we want to with Hive. Now, we can use the invoke Hive job. We can also use the new Azure HDInsight job definition function to create a new job, and then we can do start Azure HDInsight job, and then if we do that, we have to do wait Azure HDInsight job for it to conclude. Or we can use an alias and a helper function, which is just invoke Hive, and if we do a help on invoke Hive, we should see that it is it submits Hive queries to the HDInsight cluster and shows the retrieve all in one operation is the important bit. Now I like to create an alias called Hive, which simply allows me to submit like this, although you may choose to just type the default invoke Hive. When we invoke this, it does all the hard work for us. It submits the Hive query, it tracks its progress, and then it returns the results to me on the screen. I can do all kinds of other things inside this query, such as pipelining the results through into another text file. I can scrape the results from here. I can do all kinds of additional things. This is a fantastic way to submit Hive on demand in the background, and you could then use something like Azure's PowerShell automation to run these types of jobs in the background on a schedule. The sort of activity that actually productionization of workloads is suited to. If you see here on the screen, actually, you get some very interesting information coming back from this. It tells you a lot about the low-level progress from within HDInsight within Hadoop. And we can see that the results have been given to us here, exactly the same as we got inside the HDInsight portal. We have here available to us through our PowerShell. Now, if we go back to our slides, we can look at much more advanced uses of big data on Azure.
Okay, so we've described HDInsight a little bit, and what I want to do is I want to talk about some of the more advanced things that you can do with regard to big data in Azure. The first thing I'm going to show you is one of the things that we come across is this very, very consistent life cycle. Customers tend to want to do the same thing, and there's been an announcement of some really interesting services lately. Microsoft have been talking about Internet of Things and the Event Hub. So there's already a very, very big understanding that Azure can be used to ingest data from a lot of devices. And I want to focus on this aspect of being able to ingest and take in this data and then use big data technologies to query it and make sense of it and visualize it and react to it in real time and provide machine learning support. So if we look at this image, we can see that we may have telemetry data coming in from the web, and essentially we've got this fantastic messaging system within Azure, the service bus. And one of the things that we can do is we can create a service bus topic with a couple of subscriptions, and on the one subscription we may have a set of worker roles which are continually picking up these service bus messages and storing them as block blobs in Azure storage. Now, once they're at that stage as block blobs, we may want to accumulate a day's worth of data. Reports are generally based on a day, and at the end of this day, we may have gigabytes, tens of gigabytes of data, which is perfect for HD Insight to query over. So then we can apply the Azure scheduling service, and at potentially 1 a.m. in the morning, we could run a job which would effectively use a PowerShell script, or it would use a .NET, the .NET SDK to bootstrap and create an HD Insight cluster. We know that from the previous day up to that 1 a.m., we have a whole volume of data stored in blob storage because we've been accumulating all of these service bus messages and storing them as blobs. And then we can run an HD Insight job, which may be a set of MapReduce queries. These MapReduce queries would then operate over the data, and within our output we could use something like Sqroop to store the results in SQL. SQL is an absolutely fantastic format to report on, and we've got a variety of means that we can that we can use. We can use things like SQL Server reporting services, we could use Power BI, or we could use web-based frameworks like Tableau to query SQL and to generate a report. So at the following day, we would always have a report based on the previous day's results. But I think the interesting thing happens whereby within that same service bus topic that's published, we could have two subscriptions. And there's a real-time framework now which is very much integrated with the core Hadoop project, which Microsoft's partner Hortonworks is the biggest contributor to Apache Hadoop, and it's part of the HDP, the Hortonworks data platform distribution of Hadoop. And that presents a very, very interesting ideal for us because HDP underpins HD Insight, which means that we would hopefully expect that Storm becomes part of HD Insight, and so we can look at these two aspects of batch big data and real time on our big data. So using the service bus topic as a messaging conduit and two subscriptions to reading this is very, very powerful architecturally. So if we look at this then, Storm would essentially process real-time messages, and our report user may look at this data and may want to do a number of predictions on the data as well. We can also, now that we have the blobs in blob storage, we could also look at these blobs and do some semblance of ad hoc querying on this as well. So in this small circle of icons, we can see a really, really powerful sense of the fact that once we have the data in place, we can do three different things with it, from real time to predictive analytics to ad hoc querying of that data. So if we consider the way that Hadoop has evolved, HD Insight version 2 and 1 was based on Hadoop 1.0, and MapReduce was very, very central to that. So on top of MapReduce, we had this capability to write these MapReduce programs in C# or Java or Pig or Hive, but this presented some problems. It wasn't a very application-centric way of doing big data. So The newest version of Hadoop, which has now been incorporated into HD Insight version 3.0 and 3.1, has been engineered very differently. So at the lowest level, we see HDFS, the Hadoop filing system, which for our purposes with HD Insight is effectively blob storage. And then we have, on top of that, we have a cluster resource manager called Yarn. And having this cluster resource management is very, very powerful, because rather than make MapReduce central to Hadoop, what it actually does, it allows you to create applications that use the Yarn API to be able to do stuff and be able to interact with all the other nodes on the cluster. And then in between, there's an execution engine, Tez, which creates direct acyclic graphs, and that decouples MapReduce, it decouples Pig and Hive, because formerly these Pig and Hive syntax were actually compiled down into Java MapReduce code. Now, they simply use Tez to create the execution plan, which is then run across Hadoop. The upshot of this is that newer applications like Storm, the real-time application, just work with Hadoop 2.0. So we're going to be discussing a couple of frameworks, which are next-generation frameworks. One of them is Storm and one of them is Spark. They're both capable of doing real-time analysis over sliding windows of data. They can both run on top of the Hadoop stack. They can both stream messages from any source, and by any source, we don't necessarily just mean message systems. It can be things like Twitter as well. And we can analyze these messages with sliding windows. So let's consider Storm. Storm topologies are composed of things called spouts and bolts. So essentially, spouts are a way of ingesting these data, and spouts have been written to effectively pull data from various sources. And this could be message systems like Apache Kafka or RabbitMQ. It can also be the Twitter API, for example. And then bolts are then used to transform those. So we can do our aggregations in real time. The spouts pass the data that we're ingesting to the bolts, and then the bolts will actually be our application logic telling us what to do with this. So the topology is created from combinations of these spouts and bolts, as you can see, and we can mix and match them into various forms. We can group them together. We can use multiple spouts to ingest data from various sources. So if we wanted to ingest data from Apache Kafka and another source, a more Azure-friendly source called, such as the service bus, we could do that, as you can see. Essentially, the data that is emitted from these spouts are in the form of tuples, so they're highly readable. We understand tuples, we have these structures in .NET, in Java, in all high-level languages, and then the bolts will re-emit these tuples, and we'll effectively have a concentration of tuples between this topology, which will give us a good measure of being able to pass a data structure, which is very common. So one of the key attributes of Storm is this idea that you can create a topology. So if we look at this section of code, we use a topology builder class, and the spouts and the bolts that we've set can effectively be cobbled together using the set spout, set bolt method, and we can group them in various ways. So as you can see here, the first spout is a random sentence spout, and that will just generate a random sentence and emit that to a bolt. The receiving bolt in this case will be the split bolt, and that will split that sentence into all of the various words. And then lastly, that will emit effectively a tuple to the next bolt, which is a count bolt. And that count bolt will then sum up, aggregate all of the words, and keep a running total of that. So that by the time our Storm software is finished, or at interims when it wants to publish it, it will give us a complete aggregation of all of those words within the word count. Even though this is word count, there are much more incredible things that you can do with Storm. And as you can see, to submit this topology, you simply call Storm submitter, submit topology, and then that will submit it to the cluster. And correspondingly, you can also run this locally using the local cluster object. So we've talked a little bit about spouts and ingesting the data and building topologies. Now we'll talk about building a bolt. So we need to override three methods. We need to set an output collector, which we can do in the prepare method. We need to declare our output field. So we have a named field in the tuple, in this case, called word. And we also need to have our execute method. So you can see here, what we do is we get the tuple, we take the named argument, which is called message, and then we split that. That is our random sentence, and the output collector will emit each word, and will effectively have a different tuple sent to the next bolt, which is a counter bolt. And then again, one of the powerful things about Storm is that we can trace this throughout the entire Storm topology, and we can issue these methods ack or fail on the tuple. So if anything went wrong, we could fail this, and we would have the understanding that that message would have been processed all of the way through that entire topology, and it failed. And then once it gets the fail message, we would effectively resubmit that same message, so we would never ever lose data. And at the same time, we could act this message. So we have a highly transactional workflow with Storm if we want to. So one of the things that we decided to do was to create an open source a service bus spout, because we really felt that the service bus being a service where we didn't need to manage infrastructure, it's a highly available, highly resilient messaging subsystem in Azure, and to be able to put messages through this and read them from Storm is fantastic as far as we're concerned. We can support payloads up to 256K with headers of 64K. We can partition these now. We have security on the connection because we have shared secrets with our owner identifier and our shared secret key using access control services. We can have topics and many subscribers, so we can actually use SQL filters as well to discard messages. And we felt that being able to interact with the Service Bus API, as opposed to rolling our own infrastructure and creating a bunch of virtual machines for Apache Kafka or for RabbitMQ, was a much better use of Storm in Windows Azure. So what I'm going to do now is I'm going to show you a demo of using the Service Bus with Storm and Redis. And that is the new highly available Redis cache within Azure. If we look at the Azure portal, you can see that in the Service Bus, I have a Spark streaming namespace, and I have 2 queues. And each run has got several thousand messages in, and we're going to focus on the Storm queue. What I've done in advance is to read in the entire novel of Bram Stoker's Dracula, so that we can do a word count on it. And I've got my software, which is consuming the Service Bus spout. It's written using Java, so I've been. You can essentially see here that I'm using the Service Bus endpoint. Not showing you my secret, but you can see the Service Bus endpoint. You can see that I set the queue name to Storm, and essentially what we're going to do is we're going to count a bunch of words from Bram Stoker's Dracula, and we'll take a quick look at we'll take a quick look at the Azure portal just to make sure that the messages are reducing. The message count is reducing. So let's run this. We'll run it locally, although with a slight switch, we could just as easily run this in the cloud. So what's happening here is Storm is being initialized on my local machine. And Storm is underpinned by a service called Zookeeper, and Zookeeper will ensure that this is highly resilient. And it's something that HD Insight has as part of it as well. And you can see here, it might be going a little bit too fast, but you can see a whole bunch of words and word counts as Storm is picking up service bus messages and then using the bolt that we created to do those word counts. So let's just take a quick look at this, and we're at number 16,436 messages, and we're down now to 16,291. So we've got fairly good fast access now to that process. So I'm going to stop this now and just going to rerun this just to illustrate a very, very common pattern which Storm developers put in place. And I've slightly changed that word counter. So the first word counter was just pushing out these words to the console. What we're going to do is we're going to store this in using a Redis connection. So you can see that this Redis bolt is using my azurecoder.redis.cache.windows.net. So that is a Microsoft Azure service. And it's using a Java library called Jedis to interact with that Azure cache. And that's one of the great things about how Microsoft OpenTech are now driving forward all of these open source technologies, in the fact that you can interact with them via non.NET languages like Java. So if I take a view on Redis, I'll get the desktop manager up, which will take a look at that cache. So I can see I have 229 objects. I've already done a test on this, and these are each key value pairs, and you can see here that the word it was mentioned 3 times, pass was mentioned twice, only 3 times, this twice. So let's see whether we can increase that number. And I'll go back to my software now. I've changed my main method so that it's now using the Redis counter bolt here. And if I start that again, let's look at the output that it produces. Have to go through the initialization again of Storm. Connection to the service bus. And there we go. It's picking up messages. This time it's not pushing them out to the console. Not yet. Oh. And if we then try to refresh this, so I'll click reload, and we're already up to 406. Okay, so this is a very, very common pattern of using Storm, Service Bus, and Redis, and it works very, very well. Okay, so we're going to consider something else. We're very, very our company ElastiCloud has created a form of Apache Spark, which is also a big data framework which can ingest messages. And in this case, what we've done is we've enabled Apache Spark for the service bus. So everything I'm about to tell you, you can try out for yourself if you go to brisk.elastatools.com. And this will give you the capability to spin up Spark clusters. We offer a free tier, so everybody's welcome to try this. It is very, very tied to Azure. There's a lot of momentum with Spark now, and you should be able to test everything that I show you in terms of the message streaming for real-time data. So what I'm going to do is I'm going to log into a Spark cluster that I've created already, ready for streaming. Okay, so this is my shell, and I've already uploaded a special service bus streaming component that's part of Brisk, and I'm going to ingest messages from that other queue. So if I take a piece of code that I have, which is here, and I issue a simple command called spark submit, and then I submit this to the Spark cluster. And I'm going to be doing a similar form of word count here, aggregation on Bram Stoker's Dracula. So now that that is running, if I look at my Spark console, I can see that there's a lot of activity there. It appears that it's running a whole bunch of stages like we would expect Hadoop to do, but we've got an extra tab here which says streaming. And you can see what we've done is we've created 3 Azure Service Bus receivers, and very soon, as you can see, we'll start streaming messages at 5-second intervals. And we'll see those numbers change every 5 seconds. There we go, as it reads messages. And you can see on the screen, you have an aggregation of all of the words that have been counted, and that will be done every single 5 seconds. So there's a couple of things, therefore, that you can see, a couple of ways of streaming real-time data and coupling it to the service bus. So as you can see from the image, Spark, through the framework that we've created, Brisk, at brisk.elastatools.com, can enable you to ingest service bus messages and eventually Event Hub data, and then process these through receivers across a number of slaves and effectively operate so that you can create familiar Lambda syntax and read in files that are historical to the data that you're receiving and compare them, or do real-time machine learning, or do any number of things. But we've tried to tie Apache Spark to Azure, and streaming is one of the really amazing advanced features that it has. The biggest difference between Spark and Hadoop is that Hadoop works on the principle of input-output, so it uses blob storage to read files and then operate on those files. It will store intermediate files, and it can scale to tremendous levels, to petabyte levels. Spark, however, is a very good framework when the data sets are a little bit smaller and can be stored across cache cluster memory. So all of this data will be stored across a dedicated cache cluster across the Spark cluster, in the form of what they call resilient distributed data sets. So 2 copies as well. So if a node is lost, then that second copy will still be available, which makes it highly available. So now that we've looked at streaming, we're going to consider another advanced feature, which is distributed machine learning. And we're going to look at three frameworks here. We're going to look very briefly at Microsoft's newest framework, which is fantastic for data scientists and non-data scientists alike, which offers a graphical surface to be able to approach machine learning. We're going to look at Spark and show how capable Spark is of doing this, and then we're also going to look at Apache Mahout, which can operate across an HD Insight cluster and is indeed actually provided as part of the HD Insight experience. So what I'm going to do is I'm not going to delve so much into machine learning because it's a very, very big topic, and there's going to be another session, to my knowledge, on this in Azure Conf. But what I am going to do is I'm going to focus on one small aspect of it, which many customers, especially in the e-commerce market, have an affinity towards. And that is building recommendation engines. And so, very interestingly, this has a very, very simple definition, which we'll just cover now. So, to build a user recommender, what we want to do is we want to take every single item that a user U doesn't have a preference for yet, and for every other user V that has a preference for that item, we're going to work out how similar, using those items as the similarities, how similar users U and users V are. And in that way, we can work out if user V has bought items that user U hasn't, what is the statistical probability that user U will buy those items. So we'll incorporate V's preferences for those I. We'll weight them against the similarity that we're using into a running average, and then we can rank these so that we can supply the top 10. And this is a very, very common way of doing business on the web and trying to cross-sell. Amazon have made a success of this, Netflix have made a success of this, and Microsoft has invested a lot in machine learning. A lot of the Xbox services have machine learning backing. So to run a Mahout job, which is a distributed machine learning framework, we can create a PowerShell script and we can run this across a Mahout cluster. So Mahout already has a job scheduler to bootstrap. So it's fantastic in that I don't need to write any code in Mahout to actually do a very basic similarity. So I use what's called a distance measure of a similarity co-occurrence, and I can set my input files, I can set my output files, and then I can just use PowerShell commandlets, Azure PowerShell commandlets, to submit this as a job to the HD Insight cluster, wait for the results, and see whether anything went wrong. So similarly, on Brisk, on Apache Spark, you can write distributed machine learning code, and it's embodied in this idea of being able to encapsulate objects that make sense from a machine learning and recommendation standpoint. So there's a rating object that we're provided with, and essentially every single piece of recommendation will be in the form of the user as an ID, as a number that we indexed, the item as an index number, and the rating that the user has given to that, if they've given it. And that rating is something that we can calculate, or essentially it's something that we don't need, depending on the types of algorithms that we're using. So I'm going to show you a quick demo of each one of these, beginning with Azure ML. So we're going to navigate to the Azure portal, and as you can see in the Machine Learning tab, I can drill into my namespace, Azure Coder, and I simply click Sign into ML Studio, and I've already set up an experiment here, and the experiment is operating on what's called the Group Lens dataset, which is a movie ratings database with between 1,000 and 1 million rated items, movie items. So I may want to find out whether or not some person has an interest in a movie because somebody else has an interest in other movies that they've watched within the confines of the definition that we gave for a user recommender. So one of the great things about Azure ML is that it's got a lot of affinity to Azure. As you can see here with the reader, we can read things from blob storage. Then we can transform the data by projecting these columns out and getting rid of the column data that we're not interested in. We can split this data so that we can test and train various bits. We'll look at training the model and scoring models in a couple of slides forward. And essentially, we can write out the results here. So what I'm going to do is I'm going to click on this reader and click Run, just to give you the Azure ML experience. And as you can see, it begins by reading that group lens data, which I have stored in blob storage. I've configured the reader with the details. That's now finished. It will then go on to the next stage, where it will do the transformation. So it's pulled out 3 columns out of 4 in this case. It will then go on to the next stage, which is to split this data set into 2 parts, because essentially as I said, we'll be looking at this idea of training and testing data. So at this stage, it's going to be training this data using the recommender that is provided out of the box. And what we're going to be doing is we're going to be scoring and evaluating the recommender, because essentially we want to find out whether or not the model is a good predictor. So are we actually getting very, very good values back that that sort of project that idea that, and there we go, and it's finished, that project that idea that that users are, that we can actually predict accurately what users are going to watch or what they're going to buy. So as you can see here, very, very simple drag and drop workflow. I didn't need to write any code for this. Microsoft has supplied all of the things that I need to build this recommender, and I've written the output into storage, and the output will be composed of users and the movies that they should watch in the form of numbers. So I'm going to show you another demo, and essentially we looked at, we talked about HD Insight earlier, and I've created an HD Insight cluster called Mahout YX. And if we look at this cluster, it's running 24 cores in North Europe, and this cluster has access to a storage account. So you can see here I've got a storage account called Clustered. And what I'm going to do is I'm going to take a script that I've written here, and I'm going to use the cluster, Mahout YX, and I'm going to bootstrap a jar file, this Mahout core job file, which is supplied with HD Insight. And I'm going to, as you saw on the slide earlier, I'm going to define my inputs, I'm going to define my output directory, I'm going to define the similarity measure, which I need, and I'm going to also, because a lot of temp data is created in this process within the cluster, I'm going to create a temp directory. And then I can create a definition for this, so it runs on top of Hadoop's MapReduce, the Mahout job, and then I can start the job, and then I can wait, and then I can process and finish the results. So what I'm going to do is just cut and paste this and put it into PowerShell. Oops. And we started. So what we should see is that PowerShell will show me the sets of results in terms of where this is in the MapReduce cycle. So very shortly we should see some changes within the PowerShell on the screen as this gets feedback back from a service called Templeton. And this is a web-enabled service which has been produced and encapsulated within HD Insight by Microsoft and Hortonworks. And what this is doing is it's tracking the job. So I've used this Mahout job and I've given this an ID which ends in 11. And at this stage, it's gone from the state of unknown to running. And we should see that, that very shortly we get a description of what's going on from a MapReduce perspective. While that job is taking place, what I'm going to do is I'm going to talk through a little bit about these recommenders to give you a little bit more context of what's going on there. So these recommendation systems that we're actually creating now, they're more commonly referred to in the machine learning realm as collaborative filtering. So we can use ratings that have been given by users. So in the case of the group lens dataset, each of the users gave a rating on the movie. And there's a distinct variation of algorithms that we can use within this, and each of them is better at different things. So it really depends on the data which one we use and need. When we have a very large number of users, we may want to limit the set that we get back, so we can rank these according to an algorithm called K nearest neighbor. If we don't have the rating item, then that's not necessarily going to be a problem, because recommendations can be either implicit or explicit. So if we don't have that rating, as long as we have the movie number that a user watched, that's probably enough to be able to create some predictions. And we can evaluate whether or not that model that we created on recommendations was actually good or bad by using part of the data set to actually learn about the predictions, then predict the rest of the data set, and then use that part of the data set to work out whether those predictions were good or not. And in that case, it's simply comparing those two numbers of the output sets and working out the mean square error, or the root mean square error. We've considered a user-based recommender, but we can flip this on its head and we can compare items to each other and their similarities rather than the users. So I think the underlying point here is that we train these models, and that the more data we have, the more accurate these models could be. And we have this idea of training and test data. So the recommendation models have to be evaluated, and we use the majority of the data, maybe 80% or so, to train this model, and we leave the remaining 20%, which is called the test data. And in using the test data, then we can predict from our trained model that 20%. And if that 20% agrees very, very closely with our predictions, then obviously we've got a very, very good model, and we can continually feed in more data sets to make more predictions. And we have a feedback loop, which is very, very important to machine learning, so that as our data space increases, the level of predictions that we have that are sort of closer to the truth increase as well. And if our mean square of error is 0 in terms of the way that we've scored and evaluated our model, then we know that that model is perfect. So let's pause and we'll take a look at our Mahout job, which is still running. As you can see here, we have the MapReduce at 0. we'll understand that this is actually a succession of MapReduce jobs, not a single one. So we may go from 0 to 100% on the mapper and then 0 to 100% on the reducer. In the meantime, let's leave that running. It might take some time, but understand that that's actually being distributed across the cluster. And we'll move on to one final element, which we described in our model initially, that we may want to do a number of things with data. And in these advanced features, we talked about machine learning, we talked about real-time analysis of data. But the other thing that we mentioned was that we may want to do some interactive querying. So I want to show a new feature within the Apache Spark framework, which now runs on Azure through Brisk. And I think it's pretty cool. And essentially what this is going to allow us to do is it's going to allow us to run SQL commands over a data set. But as developers, the majority of us work with JSON now. And one of the things that I wanted to show was that we could, when we run these Spark jobs, we have a very rich output here, which is in the form of JSON. And you can see if we were to try to schematize this, it would actually be very, very complicated because there's a lot of things going on there. There's variations in the JSON output, and to try to encapsulate that in more of a sort of SQL framework is not going to be easy. So we're going to start a shell in Spark, and we're going to read that JSON file in. But one of the latest features is to be able to infer that schema. So as you can see, that file is very, very complicated. But what I want to do is I want to read interactively that file and see whether or not we can actually try and determine a schema despite the level of complexity. So the first thing that I'm going to do is I'm going to create a SQL context. Now, here I'm writing Scala, but you could just as easily use Python or Java. Both are supported within Spark. So what I'm going to do is I'm going to read that JSON file that I just showed you, which I've got in blob storage, and and I use a JSON file, and I've put this in the root of my blob storage, and if memory serves me correct, it's called event log _1, and that is simply the output that we get from running a Spark job. Okay, so at this stage you can see some text. It's read in some parts of the file and it understands it. What I'm going to do now is I'm going to take the JSON file variable that we just created, and I'm going to call print schema on this. And what this is going to do is it's going to take that JSON file, and you can see it's just managed to infer the entire schema of this, and it's even typed it correctly. So we have failed, which is resolved to a boolean, finish time to a long, results time integer, host string. Okay, so we've got a very, very rich JSON schema from this. So that's quite powerful. But what we can do now is we can take that JSON file and we can call register as table, and I'm going to call this, let me see, let's call this SQL table. Okay. So that's now registered, and we should be able to run a query across that. So if we take a look and try and pick out one item here. So we've got event, and let's get the distinct number of events that we could find within that JSON data set. So I am going to now use my SQL context, SQL, and we'll do a select distinct, it's called event, I think. Let's make sure the casing's correct. From, and then our table, which we just simply called SQL table. Okay. So what that's done is it's created an execution plan for that query. So I've taken something which is normally distinctly language related, but I've been able to use SQL on top of that data set from JSON. So it's quite a powerful transformation within a few lines of code. So what I'm going to do is I'm going to execute that query now, and I simply call the collect method, and that may take a minute, but that should execute that query and give us all of the distinct events within that quite large JSON file. And there we go. You can see that we've got all of the different kinds of events: Spark listener, stage submitted, Spark listener, start task, start. They've all been resolved, and we've essentially used SQL. So we've gone from JSON to SQL to a set of results that we can now use. So we'll just finally check, and our job is finished. It's created an exit code of 0. And what we can essentially do is just check to see that the output exists. So let's look at our clustered. Let's refresh that, and we've got an extra container there called mahoutyx. These are our two input files that we read in. And here you can see that we've got output, recommender, and we've got our outputs. So if we just take a quick look at these outputs, you can see that we have a whole bunch of numbers. So this is the user, 1. This is the movie ID, 2, 3, 4, and we see a whole bunch of rankings. So 5.0, 4.6. So if I was one of the users, these are the predicted movies which I would like. And in a few lines of code, running across an HD Insight cluster or using Brisk, Spark on Azure, and or using Azure ML, we have some really fantastic predictive analytics output. And that's it for me. Thank you very much.